inflection point is right at the wall. So we've looked at the case of a favorable, a zero gradient. Now let's look at a weak adverse pressure gradient. So in this case, what is now happening is we have a point of inflection that is above the wall, and we can see that the zero crossing with our second derivative is now also above the wall, and that is the point where the first derivative of u with respect to y is at a maximum, and the second derivative would then be 0 at that location. And consequently, this is a case where we have no separation, but the point of inflection is in the flow. Now moving on, we're going to get to the next pressure gradient, dp by dx, which is greater than 0, and it's what we will call a critical adverse pressure gradient, because what is going to happen, the condition right along the wall is going to get to a certain criteria where the shear stress will go to 0, and that becomes very significant. So I've also drawn out our first and second derivatives of the velocity, but the main thing is we can see that at this condition, the slope, or du by dy at the wall, has now gone to 0. And so if we compare it to the previous one, we were not at 0. We had a finite value, so tau wall did not equal to 0. However, now we have a condition where tau wall is equal to 0 because of that. And that is what we refer to as being a critical adverse pressure gradient. And that is the case of 0 slope at the wall. And that would lead to the onset of separated flow or separation. And so when the boundary layer gets to this state, it is no longer attached, and the flow enters into potentially, unless it can sometimes reattach, quite often it does not reattach, and then you get full-blown separated flow downstream. So in the case of an airfoil, this would be very, very detrimental. You would not want to have this very far up along the airfoil, because that would lead to separated flow and stall. As I mentioned, in turbo machinery it can occur, and you get rotating stall, all kinds of bad effects. The following on, let's take a look at an excessive adverse pressure gradient. That'll be the last case that we look at. So this is a case where dp by dx is greater than 0. It is an excessive adverse pressure gradient. And this is also a separated flow region. And you can even see that we have backflow, and consequently the tau wall is less than 0. So we have a negative slope at the wall. So that is the evolution of the pressure gradient. Let's go all the way back here. So we started with this case here. That was no separation. Things were nice and clean. Then we went to the point where we have the inflection point right along at the wall, and that leads to 0 change in slope, and that's why this value here is at 0. And then we move along, and we have the inflection point up above the wall, but we still have some shear stress along the wall. It's not 0. And then as we move along and we get to what we call the critical adverse pressure gradient, this is where you have 0 shear at the wall, and consequently your boundary layer at that point will separate. And then as you go further on, you even get backflow where the flow along the wall is not able to overcome the change in pressure, and consequently it starts flowing in the opposite direction, and that could then lead to massive separation. So if you're looking at something like an airfoil and you have the flow, so there we have our stagnation point dividing streamline. We can have flow coming over the top and we have flow coming over the bottom. But what would happen in the boundary layer here, you would then get the boundary layer, it's starting to form from the front, and then you get to your separation point and you get a big, massive separation region, a lot of recirculation going on in there. That would be stall. So that's very bad in the case of an airfoil. In the case of a golf ball, that's actually maybe not a bad thing because we put dimples in the golf ball and the separation point, if there are no dimples in the golf ball, it's going to be up here, and if you have a laminar boundary layer, the separation point will be up on the front. But when you put dimples in the golf ball, it actually generates a turbulent boundary layer and causes the separation point to move further downstream, removing or reducing the drag, the form drag due to the wake. But in any event, the separation point would be right in here. And that is one thing that I should say, that the golf ball idea brought this to mind. And that is the fact that laminar flow is more susceptible to separation than turbulent flow. And I should say boundary layer flow. So if you have a turbulent boundary layer, it would be less susceptible to separation than if you have a laminar boundary layer. And the reason is because when you have turbulence, you have a lot of large-scale activity taking place along the wall, and consequently the flow right along the wall has more momentum than it would if you just have a laminar flow. And that's also why we put dimples in golf balls. We put the dimples there in order to cause the flow, the boundary layer, to transition from laminar to turbulent. And the dimples are basically nucleation sites for instabilities, which then lead to transition in the boundary layer. And what that does, that causes the separation point to move back further and back here, and that causes the drag coefficient to decrease when you have the dimples and the turbulent boundary layer on the golf ball. So that's a final point about the boundary layer and how it relates if you have laminar or turbulent and the separation points. So that is the boundary layer under adverse or different pressure gradient conditions. Usually when we study the flat plate, it's always studied usually under the zero pressure gradient condition where you have dP by dx is equal to 0. You'll sometimes see that assumption being made for flat plate boundary layer flow. But just be aware that that is not always the case. And when you have different pressure gradients, it can have quite significant impact upon the formation of the boundary layer, and it can lead to separated flow, which really changes the flow regime significantly, as you can tell with the separated flow on this airfoil or what's going on behind the golf ball. So that is boundary layer flows. We've looked at laminar, we looked at turbulent, we looked at von Karman integral, we looked at Blasius's solution. In the last lecture, what we'll be doing is looking at external flows on bodies. So we'll be looking at lift and drag characteristics, which we're kind of getting into it here when we're talking about what's going on in a golf ball. But anyways, that's kind of a transition from laminar, or from the boundary layer flows into flows around other objects and bodies, which is what we're going to be doing in the last lecture.